So yeah, this is my third place solution for the efficiency track. I also followed the template a little bit. I'll give a brief background on myself, brief summary. I'll go over my approach. A lot of it's not machine learning. I'll do the feature engineering, brief training methods, and a couple of important findings. First, my background. I've been doing machine learning for 13, 14 years now. Started in college, doing like remote sensing and GIS. And I moved into sort of recurrent neural networks and reinforcement learning. Afterwards, I started computing in Kaggle, and I've been doing that on and off for 10 years. And yeah, I liked the first 2 weeks. And for this competition I joined on the last 2 weeks, I find that you get a lot, your experiments don't fail as much. After 2 weeks, usually your experiments fail 90% of the time. It get frustrating. So I really enjoyed this competition because it was pretty much everything worked. So then I'll get onto the thing. For name classes, I used rules and XGBoost. The rule in this case was just whether or not the name was in a name data set. And then I used 2 stages of XGBoost classifiers. For the non-name classes, I used simple rules like, does the token contain an @ symbol, and is the token longer than 6 characters? And that was enough to get most of the true positives. I used several external data sets for names and words, and these were used as features. And they got 0.922 in about 4 minutes, 3 to 4 minutes. I don't exactly know. The private data, the private leaderboard has not been posted, so I don't know exactly what I got. But yeah, so this score is quite a bit less than I think the first and second place solutions for the efficiency track. So yeah, probably a lot more false positives than those. Okay, and so then the approach. So first, external data sets. I used 5 external data sets. I used a zip code data set for iStreet address. So that's basically just what you think. If it's in the data set, I use dictionaries, so it's really fast to check if it's in the dictionary. And if it's in the dictionary, then it's included in iStreet address. I use 3 common word data sets for name classes, so I use a 1,000 top 1,000, Google top 10,000, and a 36,000 word data set. The 1,000 and 10,000 were sorted by frequency, so I could also use the rank in there as a feature. And I use the names data set. This is like a Facebook leak data set. And I just calculated the value counts of names. So counted how many times each name occurred. And I kept any name that occurred more than 50 times. And I used both the counts as part of the features. So for non-name classes, these are the classes that I tried. Most of them, ID number and URL personal, were the most important. The other ones only had a few examples in the training set that I could actually capture. Or I guess there was some in email too. But yeah, these were very simple rules. For example, this is the rule I used for ID number. If the length of the token is greater than 8, it's a digit, or the first 2 are not a digit and the last 4 are a digit. And that gets pretty much all of the, I mean, you're missing maybe like 10 ID numbers. Most of them were 10-digit numbers, and a few of them had like 2 to 4 like non-digit characters at the beginning. So that worked really well. And all the other ones are the same. I think like for iPhone number, those were like parentheses, like a single parentheses, which you'd have to look at the next token to get those, which I didn't do. But the one that I had was just like a phone number with dots with like periods in there, so you could split it and count each chunk and see if it matched up. So I don't know if transformers could get these or not, because there's one example in the entire training set. And so by engineering rules, you can get those. So yeah, it would be interesting to see how well they scored on some of these really infrequent examples. For the name classes, I did a 3-stage approach. First stage was to filter out if the token was in either the first name or last name data set. This reduced it from 5 million tokens to about 170,000 tokens. And for those, then I would get a window size of 5, so two tokens previous and before and after, and I would compute features on those. And I used a classifier on that to assign classes and remove some false positives. I chose a threshold that would result in 2 or 3 false negatives. So I was very, very careful not to add any false negatives into the data set at this stage because they're so important for getting a good score. And then finally, I trained a binary classifier on those 11,000 tokens that was just detecting whether it was PII or not. And then that had more features and a larger window size of 6 tokens on either side. And yeah, and that one I chose the threshold to maximize the metric score. Feature engineering, I used term frequency, inverse document frequency features for the target token, plus or minus 6 tokens. I also used TF, IDF features on part of speech tags. So these are like, is it a noun, a proper noun, or a common noun? And I used NLTK for that. And I would do that over the like segment, and then compute TF, IDF on those. And these are only used for the second stage classifier. The other type of features were just basically token-based features. Is the token the word author, or is it the word by? Some of those words were very closely associated with names, so there was important features. Also, is the token in the word or name data set? I had several name data sets. I would filter it based upon how the occurrence of the name. So I had one that was like 50,000 occurrences of that name in the data set. One was like 2,000. And so I would just check, is it in that dictionary or not? And eventually I also added rank. So which rank was the word? Was it the most frequent, least frequent? And similarly for names, how many times did the name occur in the data set? Top features, whether the first token or second token in the window is padding. These were the top 3 features actually. So I just used like a nonsense set of characters as padding if the window was at the very beginning or the very end of the document. And this was the most important feature, I think, because people usually put their name at the very beginning of a document. Also, is the token after the target token double new line? This captures the times when people would put their name at the top of the page. Is the target name mayor, which was, I think, an instructor. And finally, this is a little bit complicated. I don't know if I'll get it right, but I was originally all rule-based. I wasn't even using XGBoost, so I had these kind of weird data sets. This one was basically removing common words from the names while keeping very common names in there. So you take the top 10,000, top 1,000 words, remove names that occur more than 50,000 times, and then remove that list of what's remaining from all names. And that was the first and last name version of that were top features. So that's that training. I did 8-fold random CV K-fold of XGBoost. I used an older GPU. It's really, really fast. I chose 2 folds and I blended those. So I started out using 5 models, but 5-fold, but then in the end I only used 2 because it's about the same score. I did parameter tuning at the very beginning and then stopped doing it. So definitely could do more of that. As I added lots of features before and never changed the parameters. Important, interesting findings. You can get 0.84 public score in under 30 seconds using rule-based methods only. So I used no XGBoost. The rules were things like, is the first token a first name and then is the following token a last name? And if it's that, then you can decide that, okay, this is a first name. And so there's a bunch of rules. It gets kind of complicated, but you could get that with no machine learning at all. And so that was one of my first solutions. That was pretty interesting. And finally, the solution isn't optimized for time. In the current 4 minutes can probably be reduced to 3 using like multiprocessing, job-lib, and reducing the number of iterations for the classifier. Currently, I'm using like 1,500 iterations, and I can probably get down to like somewhere like 1 to 300 iterations, and that'll give the inference time speed up by like 5 times at least. And all the feature generation is single-threaded, so that can also be sped up. And that's it. Any questions?